Hi, welcome to week 9 of the course Combinatorics 2 at Stockholm University. And so this week we will consider planar graphs in the first part and then Hamilton paths in the second. And so planar graphs is a really beautiful area and subject here. So what is this about? So for instance, here we have a graph. So this is an abstract graph having 1, 2, 3, 5 vertices and 1, 2, 3, 4, 5, 6, 7 edges. Now if you draw it, you might say, well, that's not a good drawing, right? I mean, if you want to draw it in the first place, you can do it maybe better by doing it like this. Maybe here you want to connect it like this. Okay, so this is clearly the same graph, but it's just a different drawing. And this is nicer. Why is it nicer? Because now the edges do not intersect. And so this gives the following definition. If you have a graph, you call it planar if it's possible to find a drawing in the plane where the edges do only intersect in vertices. They don't intersect in the middle somewhere. And so this is a very nice class of graphs for many reasons, obvious reasons. So are there any graphs which you cannot draw in the plane in this way? And let's look at K5. You might say, why K5? Well, what about K4? Here's K4, but if you take that away, you have K4, and of course you can draw it in a planar way. But now let's try K5. So, okay. That means like 5 vertices and every 2 edges are connected. Try this. That's not good. That already gets that here. They have to connect these two, so we do that. Now we connect that. That looks good now. Right, so anything missing here? We can also connect this. Now we have a problem. We cannot connect this vertex with that vertex. So somehow something's going wrong here. We cannot draw K5 into the plane in that nice way. So they might give the answer. I mean, the question which comes up, can we decide whether a graph is planar? I mean, can we say at least something about planar graphs? Maybe that cannot be too big if there are too many edges. It seems like if there are too many edges in there, somehow you cannot draw them without intersection. And indeed, that is true. So that's something you want to prove. And if you think about it, just showing that, for instance, in this case, it's not possible to draw it in a planar way. I mean, you will probably start playing around like I did, but finding a rigorous argument is not at all obvious. And this is one of the powers of the following formula, namely Euler's theorem. So Euler's theorem is arguably one of the most beautiful formulas in all of mathematics. So this is really among every top 10 list you will find of the best and the nicest and the most appreciated and used theorems in mathematics because it has so many different generalizations and it's so useful. Okay, so what does it say? Well, you have a graph which should be connected. There's also a version if it's not connected. Most importantly now, it's a planar graph. For instance, the one you've seen already up there. And now what you do is you choose some planar drawing. For instance, you choose that one here. And now R is a set of regions. What do I mean by region? Well, let's look at this graph here. Well, for instance, this is a region, then we have this region here, and we have this. So how many regions do we have? We have 4 regions. Important fact, don't forget the unbounded region. There's an unbounded region. And here I have a different drawing. And actually it looks kind of different because, for instance, here there's this one edge sticking in that bounded region, where here that edge sticks now in the unbounded region. And in more generality, these drawings can look quite different. Okay, we choose one planar drawing. We look at the set of its regions. And now I claim that the number of vertices minus the number of edges plus the number of these regions is always equal to 2. So here, let's look at this. We have 1, 2, 3, 4, 5 vertices minus 1, 2, 3, 4, 5, 6, 7 plus the number of regions was 1, 2, 3, 4. Let's just hope I'm right. But of course you get like minus 2 plus 4 is 2. So this is a really, really beautiful formula. And now what can you get out of this? So first of all, what we see is that the number of regions can be computed from the number of vertices and the number of edges. So it's 2 minus the number of vertices plus the number of edges. That means that even if you have very different looking drawings of the same graph, different planar drawings, the number of regions will always be the same, because it always should just depend on the number of vertices and number of edges. One more thing here, very importantly, don't use this theorem if it's not planar. If you don't know that it's planar, what should be the regions in the first place? It doesn't really make sense to talk about regions in that case. So really, this is really, it's very important that you are in this situation. Okay, so what is the proof idea? So one just does induction on the number of edges. And if you have a very small number of edges, it's easy to check that this formula holds. So the base case is simple. The induction step is the non-obvious one. So there are two cases. Let's do the first case. The first case is you pick out an edge, and so you pick out an edge, and you remove that edge. Now what happens is, and that's the first case, that the graph becomes disconnected. So splits into connected components. So for instance, this one lies in a connected component, and this lies in a connected component. Now, and the picture is in some way accurate because there cannot be any more edge connecting these two guys somehow, because otherwise it would be connected. So, but if you take it out, it should become disconnected. So that's the only way how it essentially looks like. And now we use induction. So why can we use induction? Because the subgraph of a planar graph has to be planar. Because, I mean, if you can draw the big graph in the plane, you can definitely do it for the smaller one. And so here we have that for that graph, we use our induction hypothesis. So let's call that G1, and that would be like E1 plus E1 minus E1 plus R1 is equal to 2. And here we would have the other formula, so for this one and for that one. Now we just add it up. What do we get? Well, the number of vertices plus the number of vertices here together give you all the vertices, so this gives you just V. Now, here we get minus the number of edges of E1 plus the number of edges of E2. How many edges are these? These are nearly all of them except one. So minus, namely that one here. Right? And so finally we add up these two regions. So now we have to be very careful. There are all these bounded regions in here, and there's one unbounded one. So we're counting all these bounded ones, we're counting all the bounded one here, so this gives you all these nice bounded regions. But the unbounded one was counted here, and it's also counted here, so it's counted twice. So we have to subtract. So it's counted twice. So this means like we have to plus 1, of course. Just thinking like we're counting twice. So this means like we have the bounded regions in here, the bounded regions in here, and the unbounded was counted once here and once here. And so the unbounded region is counted twice. So we have one too much here. But that's fine, because adding 2 and 2 together gives us 4. And now we just cancel the +1 here, and the +1 here gives you +2. If you cancel it out, you get the formula. Okay, sorry if it's a little bit fast. So definitely, you know, in any case, I tell you, look it up in the book again. But this is the idea here. Now what about the second case? The second case is that, again, you have your edge, and you take it out. But now, the subgraph you get is still connected. That's the second case. So I don't know how it looks like. You have all this going on here. And like this, and so forth. Any kind of graph. And so by induction hypothesis, after you take it out, because the remaining subgraph is still connected, you can use the hypothesis. So we have the same number of vertices, but there's one edge less. Now, what about the number of regions? Well, if you take this out, so I claim, let me just write down what I claim. I claim that this is, so the number of regions will be the number of regions of a whole graph minus 1. And so why is this? Well, the number of, if you have, what we see here, what's happening is that you have this unbounded region here. And now if you take this one out, this bounded region is going to merge with that one. Which means that we have one bounded region less. So if you take this edge out, you know we have this bounded region here, unbounded region here. If you take that edge out, this bounded region will just, will be flooded. So essentially, there will be one bounded region less, and therefore the subgraph that you get by taking out this edge will have one region less. So we have this formula here. And again, if you have +1 here and -1, it cancels out, and you get the formula. So I apologize if it's too sketchy, but I hope you got some idea about the proof, and so I encourage you to read carefully about this again. Okay, so let's look at an application. So here's a following corollary of this. If G is a loop-free, connected planar graph with at least 3 edges, so not too small, then the number of edges can be at most 3 times the number of vertices minus 6. So this proves the observation we kind of already made by looking at just at some examples, that if there are too many edges, then everything gets so dense and crowded that you cannot find a planar drawing anymore. And so how do you prove such a result? Well, Euler's theorem is really the clue. So here's the proof idea. So assume you have your graph here and you draw it. You are able to draw it into the plane like this. So what you do is we look at all the regions. So we have a region here, now the region here, now the region there, and of course don't forget the infinite region, the unbounded region. So 4 regions here. And so what you do is we look at each of the regions, let's say this one here, and we walk around the boundary. So we walk along the boundary, and every time, for every edge, we put a 1. And maybe again I can use some colors. So here we use that region, and we put a 1 here, and a 1 here. Now if you go to that region, 1 here, and 1 here. Now we go to that region here. Again, we start here, so we have maybe 1 here, another 1 here, another 1 here, another 1 here, another 1 here. Now comes this edge. We're walking like this, we're walking in here, so we have a 1 here, and now we walk back again. So you get another 1. And then we're back to where we started. Okay, so watch out when you have like things sticking out like here. And now comes the unbounded region. Well, now let's maybe again start here. So now we go along this. So 1, 1, 1, 1, 1, 1. And now, again, we go here, 1, and go backwards again, 1, along here, 1, and finally we're back here. And so what we see is something similar as we've seen before. We get 2's everywhere. So we know now that 2 times the number of edges equals, well, what did we do? Well, we're going looking at each of the regions. So for each region, let's say, let me see what notation I want to use. Let's say region, just call it G. So G, a region. And for each such region, well, what did we do? We are walking around the boundary, and so this is called the degree of a region. So what's the degree of a region? Well, if you have a bounded region, something like this, well, the degree is the number of edges on the boundary, so it's 4. Of this G is 4. Now, if you would have instead something bounded region, but maybe something more complicated, like here sticking out something, then again you walk along the boundary, and in this case we have to count this edge twice because we use it twice, and so it must be 1, 2, 3, 4, 5, 6, 7, 8. I hope this is correct. So this is G is 8. G degree would be 8. And of course, we can do the same thing for the unbounded region. In that case, for instance, let's do an example. Maybe that example here. In that case, we look at the unbounded region, which means everything else. And then the going along the boundary, 1, 2, 3, 4. Would be the degree would be 5. And of course, as in the other example, if there's something sticking out, they would have to count that several times, so 2 times, because we use it twice if we walk along the boundary. So this is what the degree is. And so this is precisely what they're doing. So this is just the sum of a degree has to be equal as 2 times the number of edges. Okay, so let's look at these examples here. What can we say about the degree of in a region? Well, there are essentially like 2 cases. One case is that it's bounded, like here. And if you think about it, the smallest region you can think of has 3 edges on the boundary. It's like the smallest one you can think of. In this case, the degree of that region would be 3. So for every bounded region, it's completely clear that the degree is always at least 3. Now what about the unbounded region? Maybe you have a really complicated looking graph, but so with a really complicated looking graph, I don't know, but the unbounded region, now the degree looks what happens here. Maybe you have something sticking out. So it only looks at what happens on the boundary here. How many edges do we have? Well, don't jump to any conclusion, because there might be some we have to go once around it. So you might think at least 3. Well, that's okay, but what about this graph here? Well, such a graph has the degree of the unbounded region is 1, 2, 3, 4. And so it would be possible that you have maybe this little graph here. The degree of the unbounded region would be 2. But that is not allowed. By this assumption, you have at least 3 edges. So by looking at both these cases, we see it has always at least 3 edges. So the degree of a region is at least 3, and that means it's 3 times the number of regions, so the number of R. Okay, and now, so this is like general for, well, you have the planar graphs in this case. So, well, for planar graphs, but now comes the clue. The clue is that we use Euler's formula. So what do we know about R? Remember Euler's formula, the number of vertices minus the number of edges plus the number of regions equal to 2. So the number of regions was 2 minus the number of vertices plus the number of edges. And so what is this? This is equal now to 6 minus 3 plus 3 times the number of edges. And so now we look on the left side and the right side. And what we get is now bring 3v on the other side and the e's on that side. So we get number of edges is at most 3v minus 6. And that's precisely what we claimed. Okay, and so we had some nice important exam applications, and so here's one application, namely, let's look at K5. So K4, you've seen that we can easily draw K4 in a planar way, so K4 is planar. K5, try it, you will have lots of trouble doing it, and the reason is it's not possible, so K5 is not planar. One of those really small graphs which is not planar. And why? Now we can give a nice proof, namely how many vertices? All 5. How many edges? 5 over 2, which is 10. So, what do we conclude? Well, what is 3 times e? 3 times 10 minus 6. Of course, the other way around. 3 times 5 minus 6 gives is 9. But 9 is not is bigger than is smaller than 10, and so we know from what we just seen is like that the number of edges is at most the number of 3 times the number of vertices minus 6. In this case, this would mean that 10 had to be at most 9, which is not true. So it cannot be planar. So this is a loop-free connected graph. It has at least 3 edges. So we can use that, corollary in the case if it would be planar to see that we get a contradiction, so it's not planar. And so this is a really nice, rigorous, clear proof why K5 is not planar. So this is very important. What about K33? Well, let's just try the same thing. How many vertices? 6. How many edges? Well, for each one you have 3, so 3 times 3 is 9. So let's check it out. So 3 times the number of vertices minus 6. What do we get here? Well, 12. And what is the number of edges? 9. So what can we conclude? Don't jump to the conclusion that this proves that this is now maybe planar or not planar. Well, you cannot say anything. So, for instance, like what we just proved, if it is planar, then 9 would have to be at most equal to 12, which is true. Now, I didn't say anything about the converse. If you know that this inequality is true, it doesn't necessarily mean that it has to be planar. Actually, we don't think it is planar. And so we cannot use, we just simply can't use the previous corollary to show that it is not planar. So it's just no use here. That what we get out of here is, well, we cannot use the previous corollary. That's all what we can say. But still, it is not planar. And so what it uses is just, what we have to do is you have to look into the proof of the corollary and just refine it a little bit. You have to use more about K33. And then the same kind of arguments actually can be used to show that it is not planar. So this is something I really want you to think about it. I won't do it here. And this is done in this example. So read it very carefully. And maybe you want to think first about it. So the important property you want to use is that if you have a bipartite graph, so if you have a bipartite graph, and you think about maybe you could put it in a planar. Maybe it would be planar. If it would be planar, you could find a plane drawing, and then look at a region in there, a bounded region maybe, and look at that so-called boundary cycle. So I mean, walk along the boundary. Maybe you want to choose a cycle on the boundary. So a cycle in a bipartite graph, that's something we actually know something about. Namely, if you start out here, and then you go here, then you maybe go here, maybe go here, and then finally we can go backwards. But how many steps do we at least need in order to close it up? Can we do it in 3 steps? Remember in that corollary what we used was that if you had the smallest region used at least 3 edges. Now here we can say a little bit more. In fact, here you always have to use 4 edges because a cycle in a bipartite graph always has an even number of edges. And that, if you use that stronger observation, you can prove that this is not planar. So please have a look at that example. So we just looked at K5 and K33, and these are not planar. Now, the amazing fact is the following, that if you have a loop-free graph, then G is not planar. Well, we know it's not planar if it's K5 or it's K33. Also, if K5 or K33 would be a subgraph for your graph, that bigger graph also cannot be planar because the smaller one isn't. But the important thing is, if it's not planar, then this has to happen. So there must be a subgraph which essentially looks like K5 or K33. Now, what does essentially looks like mean? It means it's essentially K5 with a lot of extra vertices on the edges, or K33 with lots of extra vertices on the edges. But just to make this really precise, so that we really 100% understand the theorem, let's just define that notion here, so homeomorphic. So we say that G1 is homeomorphic to G2. If there exist 2 graphs that are isomorphic, that are isomorphic to each other, such that the graph interested in G1 is just given by a bunch of so-called elementary subdivisions of G1 tilde, and the same thing for G2 coming from G2 tilde. And now what is an elementary subdivision? An elementary subdivision is elementary. Namely, you just add a vertex on the edge. So you have this graph, and now maybe I want to add a vertex here, and maybe then another vertex here on that edge, and maybe here another vertex on that edge, and so forth. So just putting lots of bunches of vertices on the edges. And so homomorphic means that you have your graph G1, and that comes from a graph where you just put in lots of vertices, and the same thing for G2, and the 2 graphs you come from are really isomorphic, are really the same. So essentially you're starting off with the same graph, and you're adding lots of vertices to it on the edges, and then what you get, this will all still be homeomorphic. And so let's look at an example. So here's G1 and G2. And, well, are they isomorphic? No, they are not. There are much too many vertices here compared to there, but I claim they are homeomorphic. So why? Because, well, if you think about it, just take away this one here. So I claim you take this guy here, G1 tilde, and let's make this a little more complicated by actually choosing a different diagonal here, namely this one. And so what we see is that this is now an elementary subdivision. You take this graph and just add a vertex in here. Now here we can do the same thing. We can remove lots of vertices here. Namely, I claim that if you take G2 tilde, and now you put just this vertex here, and this there, and there, and there, to that after a while you get this graph here. And now what about these two? Well, are they really different? I mean, they look different, but now we've already seen that. These are isomorphic graphs. So these are isomorphic. They're really the same. And therefore, by our definition, these two are homeomorphic. Okay, so I hope this example kind of makes the definition a little bit clearer. Okay, so how can you use Kuratowski's theorem? Well, let's illustrate it here. We have a graph, and I claim that this graph is not planar. Now, how can you prove this? Well, what we do is we identify a subgraph which is homeomorphic to K5. So let's do this. First of all, need a subgraph, and I claim we remove a few edges to make this look simpler. So we remove that one here. And we remove this one here. And that one. Okay. So this is now our subgraph. I claim this graph is homeomorphic to K5. Why is that? Because you see here we have a vertex of degree 2, meaning I claim that this guy comes really, you can really remove this vertex. You get this edge, and they put a vertex in there, and they come here. So this is a graph. So we get the subgraph we were talking about as an elementary subdivision of this graph. And now, again, see here something of degree 2. Let's remove this one here. And again here. Okay, and this is now our K5. 1, 2, 3, 4. We have 4 vertices, all of them are connected, and now we have one more vertex, and that is connected to all the 4 of them. This is K5. Meaning, we found a subgraph in there, which comes from elementary subdivisions of K5. Meaning that it's homeomorphic to K5. Just from the very definition here. Maybe you are now a little bit confused, but you know these two are homeomorphic. But actually, also these two are homeomorphic. This is what I really used here. Yeah, of course they are. Namely, if you really want to make things complicated, so we had our graph G. In there, we had our subgraph G prime. And I claim that this subgraph now came from, so let's draw this again. So we have graph G, so this is our graph. We have in there a subgraph, G prime, subgraph. And now, this came from elementary subdivisions of K5. So, an elementary subdivision is a special case of homomorphism. And now, just to make this again clear, why is that the case? Well, simply because of this. You can write K5 here, you can write K5 here. This is, of course, isomorphic. It's the same thing. Not doing anything, not doing any elementary subdivision is also allowed. This is not really clearly stated in the book, but of course, if you a sequence of elementary subdivisions can just be the identity, just doing nothing. That's also, of course, just an, you don't do anything, that's fine. And so from this picture, we now see that these two are homeomorphic. So in other words, elementary subdivisions are a special situation of a homeomorphism. And that means what this shows is that Kuratowski's theorem tells us that the graph is not planar because we found a subgraph G prime which comes as an elementary subdivision of K5. In particular, it is homeomorphic to K5. It's much stronger, and that shows that no chance that the big graph is planar because K5 is not planar. and therefore also a G prime is not planar, because if you could draw something which you got from putting in lots of vertices on the edges, if that would be planar, then you also get that one would be planar, but it is not. Okay, so please read examples 11.7 and 19 and 20, 21, 22, and the proof of theorem 11.6, which is very, very important that you really understand the proof, not only the result.